In Lab 3, we discussed the forces of a black hole. We created an orbit of a star around a black hole, and we were all assigned different trajectories based on our Georgia Tech emails. We then wrote code in GlowScript in order to model the trajectory and calculate the net forces acting on the star at different points in its trajectory. We also used our code in order to calculate the mass of the black hole. In this lab, we continued to apply Newton's second law, but this time we added an aspect of curving motion, since the trajectory was elliptical. In terms of curving motion, there are different aspects of the net force acting on an object. One aspect is the force acting in the parallel direction, which can be written as F net equals d times the magnitude of p over dt times p hat. Another aspect of the force is the force acting in the perpendicular direction, which can be written as F net equals magnitude of p multiplied by d times p hat over dt. The total net force on an object is the sum of the forces acting in the parallel and perpendicular directions, which can be written as F net equals F net perpendicular plus F net parallel. When we look at our code, we see the seed, which is my Georgia Tech email, which created my individual trajectory. Then, we can slide down to the things that we had to modify. Our gravitational constant g is 6.7 times 10 to the negative 11th. The mass of the star was given to us as 2 times 10 to the 30th. Then, we had to set our delta t as the number of seconds in a day, which is 86,400. Then, we had to calculate our initial and final momentum vectors. Since the formula for momentum is mass times velocity, we had to do star times the star's mass multiplied by its v initial for p initial, and then the star's mass times its final velocity for p final. We then defined delta v as the change of velocity being the final velocity minus the initial, and then delta p as the final momentum minus the initial momentum. We then calculated dp dt as being the change in momentum over the change in time. According to Newton's second law, this net force is going to be equal to dp dt. We then have to split this into our different components, our parallel and our perpendicular components. First, p hat, which gives us the direction, is equal to our initial momentum divided by its magnitude. Then, our d mag p dt is equal to the magnitude of our final momentum minus the magnitude of our initial momentum divided by our change in time. And then, finally, our force in the parallel direction is equal to p hat times d magnitude of p dt. Then, we define this as F net parallel, which is equal to dp dt parallel. Now, we calculate the perpendicular force, where we can say that dp dt perpendicular is equal to dp dt, which is the total net force, minus dp dt parallel. We then define F net perp as dp dt perp, and then, finally, we write codes to calculate the mass of our black hole. We define our position vector as being the origin of the star minus the star's position, and then we write the formula for the mass of the black hole as the magnitude of our net force times the magnitude of our position vector squared divided by our gravitational constant times the mass of the star. Finally, in order to model our forces, we created arrows to depict our forces. We can see this once we run the code. When we look at this elliptical orbit, we can see that the magnitude of the forces, as can be seen by the arrows, increases and decreases based on the position of the star. We can also see that the mass of the black hole is not constant all the way throughout, which we'll discuss. We can also see the printed total F net parallel, and F net perpendicular. As I mentioned earlier, as we could see in our simulation, the mass of the black hole is not constant throughout. This can be attributed to numerical errors within the trajectory itself, and since we derived the mass from the trajectory data, the numerical errors cause the mass to fluctuate by a small amount. What does it mean? How exactly do the parallel and perpendicular components of net force differ from the parallel and perpendicular components of the rate of change of momentum? When looking at it, they look very similar, as Newton actually wrote his second law to be the rate of change of momentum is equal to the net external force on an object. However, we can look at these two to be in a codependent relationship, or cause and effect. A net force acting on a system is what causes the change in momentum, meaning that if we want to change in momentum, we will need a net external force acting on the system. Therefore, net force is what causes the motion, while momentum is what keeps the object moving. If the black hole in our simulation was removed and replaced with another one, and the motion of the star remained unchanged, we could not find a value of the mass of the black hole that was different than the original one, due to the fact that the only data that we have is position data, and we know that the trajectories are the exact same. Since we know that the black hole is the only force acting on the star and the trajectory is unchanged, the mass of the new black hole cannot be different from the first one, since the trajectory is the exact same.